Hi, welcome to Dynamics. So in today's class, we're going to be talking about Chapter 13 for the first time. We spent 5 weeks working on Chapter 12. We're going to spend 1 week working on Chapter 13 because that's just how it goes. Today, we're going to be talking about Newton's equations of motion, his laws of motion, and that includes using the equation F equals ma as it applies to rectangular coordinates, or the XYZ coordinate system that you're familiar with. So getting into class for today, the only announcement that I have for you is that the NIU program here at Warwick Valley College is supporting a job and internship fair on this coming Wednesday, February 19th from 3:30 to 5:30 p.m. in the WTC lobby. So if it's at all possible for you to get to campus, I'd highly recommend that you participate in that event. It showcases typically somewhere around 15 companies local to the Rockford area that are interested in hiring students in our program. As a student in Dynamics, you are in the perfect place to submit your resume to these companies and potentially get an internship and ask questions about potential employers once you finish your degree program. So really, really exciting opportunity that you have. It puts yourself out there. It helps you work on your networking skills and helps you basically learn how to talk about yourself to other people, which is really important when it comes to getting that job. So we're going to do a few things in this presentation. First thing is academic integrity, review a little bit from week 5, and then we're going to move into Newton's laws and the equations of motion in the rectangular coordinate system. So first things first, I just want to mention a few things about academic integrity because I think it's part of my responsibility as a faculty member to make sure that you understand the expectations. So in the link in the slides for today, you have a link here for the student handbook. If you haven't looked at that before, it's really important that students understand what's in there. I'm not saying you have to read it cover to cover, but at least get familiar with the topics that are in the student handbook because it outlines your rights and responsibilities as a student at Rock Valley. One of the most important sections of it, it comes around academic integrity. It basically lays out the expectations for students as serious and honorable scholars so that your education at Rock Valley carries weight once you enter the workplace. When I think about this, I think about 3 key things that I want you to get out of this message. The first one is I consider that academic integrity is a critical part of the learning process. If you don't approach your learning with the highest standards for academic integrity, then you're putting your entire education at risk. The second point is that as a faculty member for the college, I have a responsibility basically to report any instances of academic misconduct that I find. I am not out there actively looking for signs that every student is cheating, but if I observe something, I have to act on that. And then the third one is, as outlined in the student handbook, you have both rights and responsibilities when it comes to any instances of academic misconduct. And those rights do include the right to appeal a decision from a faculty member by reaching out to the Dean of Students office. When it comes to cheating, there's lots of different types of cheating. In my opinion, the one that I have seen most often is students that are trying to use resources that are not permitted during online assessments. I provide lots of resources to help you learn. I encourage students to collaborate while you're learning. But when you take an assessment from me, I expect it to be your work and yours alone. This is the primary way that I assess whether or not you're able to make sense of the topics that we discuss in this class. So you have to recognize that when you don't follow those expectations, there's lots of things that are wrong with that. First one is that our society sees that cheating is the same as lying or stealing. So it's at about that same level there. It causes a lot of stress, and that's stress in you, the cheater, that you're afraid that you're going to get caught. You're afraid of what the consequences might be, but it also causes a lot of stress for me. As soon as I suspect that a student has engaged in academic misconduct, there are a lot of steps that I have to go through to close that situation. And it ends up adding a lot to my workload. And then there's the stress of having to actually talk with the student about it. It's not a pleasant experience for either of us. And then the entire process of submitting the report to the Dean of Students office and accommodating an appeal if one is filed. Obviously, cheating can be embarrassing if other people find out, and quite often it's also followed by feelings of shame because you know what you did was wrong. Cheating is also unfair not only to you but to others as well. If I have a student who worked really, really hard to earn a B, and then I have a student who cheated that got a B, those B's aren't the same. And so it devalues the value of the education for both students. It's unfair to you because now you're not taking advantage of the education opportunity that we have here at the college. Cheating will also hamper your progress. You probably already figured out that a lot of what you learn in college builds on itself. So if you cheat on a foundation level assessment and you haven't actually learned the content, it's going to continue to come back to you and haunt you later on as the content gets more complex as we get further into the semester. It's disrespectful. I've already talked about the additional workload that it puts on me to have to investigate and report instances of academic misconduct. It also kills trust between the teacher and the student because it's more difficult for me to trust you in future endeavors if we have a past history of cheating. And then the last one is cheating can very easily become a habit. You might be encouraged or tempted to cheat because it saves you time for a particular assignment. But once you justify it to yourself once, chances are you're going to find it a little bit easier to justify it to yourself in the future. And unfortunately, the more you cheat, the more the consequences are going to be when you eventually lead to failure, whether it's getting caught in cheating in college, or if you're able to make it out of college, getting into the workplace and you just aren't competent in what you should know, and then you get found out as being an engineer who isn't worth the degree that you supposedly earned. The good news is as yucky as it is to talk about the negative consequences of cheating, there are a lot of alternatives available. And this is really what I hope that you're going to take home from this. I am here to support your learning. It's the reason why I became a teacher. So obviously I want you to reach out to me if you're struggling in the course so that we can help you understand the content. You also have to recognize that Rock Valley has a lot of tutoring support available for you. That includes tutors on an on-campus tutoring center, and then it also includes online tutoring that we hire out. There's also a math lab and a writing center on campus to try to help you with your coursework. The next thing is that I think a lot of students are tempted to cheat because they're just not managing their time wisely. I recognize that you're all really busy. You're working a lot of hours, you're taking a lot of classes, and you're also supporting your loved ones outside of work and school. But if you're waiting until the last minute to get assignments done and you recognize that there's no way you can get them done before the deadline, the temptation to cheat is going to be that much stronger. So by managing your time wisely, breaking up your assignments into smaller pieces throughout the week is going to be much, much better than waiting until 11 o'clock on the last day before the assignment's due. You also need to develop your other study habits. Maybe you're finding that you're taking too long to study. What you thought was going to take an hour ends up taking you 2 or 3 hours. That might be because you're not using effective study strategies. So if you meet with me, I can help you with time management and also help you find the best ways for you to learn the content. So please reach out so that I can help you with that. Another common reason why people are tempted to cheat is procrastination. And our personal and success counselors can help you with a variety of mental health issues with both short-term counseling, and they can also make referrals to long-term counseling if that's warranted in your case. Another avenue of support is that you can register with the Disability Support Services Office as needed if you have a documented disability. By getting the accommodations that you're entitled to, it can make it a little bit easier for you to learn the content. Another one that I think is underutilized by both faculty and students is there are alternative ways for you to demonstrate your learning. One of the common reasons why students cheat is that they're worried about how well they're going to do on a test or an exam. And so they try to find ways to cheat, whether it's an online exam or a paper exam, because they know that they're not going to be able to demonstrate their learning in the traditional manner. In our class, I recognize that stress during assessments is very high for a lot of my students, which is part of the reason why I provide you with doing additional work and with reassessments afterwards if your assessment doesn't meet your goals. The last two, I think, are really important ones, but are difficult for a lot of students to really consider seriously. The first of those is sometimes it is going to be necessary for you to reevaluate your priorities. I know you're working a lot of hours, you're taking a lot of classes, and you've got a lot going on in your personal life, but there's only so many hours in a day. And sometimes it becomes necessary to evaluate those priorities. And if you have to work to eat and you have to take care of your family because you love them, there are times when you might have to alter your education goals in order to do what's most important in your life. So instead of taking 4 classes a semester, maybe you only take 2 or 3. It will extend your graduation date, but you're going to be much better off in the long run for doing so. I can help you with that priority brainstorming session if you would like. I've had conversations with students about this a lot over the years, and there hasn't been a single instance where that conversation hasn't ended up with the student in a better place in the end once they've settled things through. And then the last one is just to recognize that you're here to learn, and learning is a process of making mistakes and learning from those mistakes. A lot of times students in an engineering program are very highly capable students, sometimes even students that didn't have to study very hard in high school. And they get to college and recognize that they really have to bolster their study habits. So you're going to make mistakes. You may even do poorly on an assessment or even in the class overall, but use those as opportunities to learn. Don't think that you're a failure. You got to rephrase that in your mind and turn it into positive. I just haven't learned it yet. And then seek out help when you need to. So I hope that these alternatives give you some food for thought as you're struggling with the course, whether it's this one or another one that you're taking, that there are really a lot of alternatives out there, and we're here to support you. So please just reach out to someone for some help. So I did offer the in-person students a survey for the week 5 homework. I have posted a couple of problems that we worked through on the materials page for this class, the week 6A class. You're welcome to fill out the survey, but I just want you to know there's going to be a little bit of delay between when you fill out the survey and when I might be able to post some additional support. Otherwise, what I would really recommend to you is to reach out to me if you have questions. I do post hints and problem-solving tips and examples online. And then after the deadline, I do also make available a lot of the solutions for the problems in the homework to help you. But if those resources aren't doing it for you, feel free to reach out and I'd love to help you out with that. So for today, we're going to be starting chapter 13. We're going to talk about it today and then again in the next lesson. And then that's going to be it for chapter 13. It's a much shorter chapter than chapter 12 was for us in the beginning. When I think about what I want you to learn out of chapter 13, the first 2 objectives are actually review of objectives we discussed in statics. So the first one is making sure that we understand how to convert between mass and weight. We're going to be using Newton's second law of motion to do that. And you have to remember the ins and outs of doing that conversion process because we're going to be using both weight and mass for the rest of the semester. So being able to easily convert between the two is a really essential skill for dynamics. The next one is, again, a review of statics, drawing and interpreting free body diagrams of a particle. So we learned all about free body diagrams and statics. We're going to be using everything that we learned again in this class, and then we're going to be building on that. After we review those two objectives, then I have two brand new objectives that we're going to be talking about today. The first one is a brand new type of diagram, not drawing, a diagram. It's called the kinetic diagram. So we're going to learn how to draw one and how to interpret it. Right now, kinetic diagrams are going to be very, very simple, but it's also very easy for students to mess up with this when they get to that question on the assessment. So pay attention. It's a simple diagram, but it's something that you do need to think about a little bit. And then finally, the main objective for today's lesson is just using Newton's laws of motion to solve some problems involving particle motion. So we're going to discuss that as well. So what are Newton's laws of motion? The first one is the law of what I call the law of inertia. This is the one that says an object at rest will stay at rest unless it's acted upon by an outside force. So that basically means if I'm sitting in my chair right now, I'm going to keep sitting in my chair until somebody comes by and gives me a shove and makes me move. The other part of this is an object in motion will stay in motion unless it's acted upon by an outside force. And this, in essence, is Newton's law of motion, right? In statics, we talked about equilibrium. So whether I'm sitting still in my chair or I'm a child on a swing, we're going to keep moving on the swing until somebody comes by and gives us a shove, and then now we go higher than that. But both of those talk about this concept of inertia, which is going to come up a few times for us this semester. Newton's second law is F equals ma. So force is equal to mass times acceleration. It's really important in dynamics and in physics in general that you don't look at equations like this one as F equals ma, but that your brain registers what each variable stands for. So the summing symbol there means that we're going to add up all of the forces. The little arrow above the F indicates that it's a vector, so we have to worry about magnitude and direction. And then that's going to be equal to mass, the amount of matter in an object. That is a measure of the inertia of the object, and then times the acceleration. And again, that acceleration has an arrow over top of it because acceleration is a vector quantity. So we need to look at this not as F equals ma, but force is equal to mass times acceleration. And then Newton's third law is the law of action and reaction. So for every action, there's an equal and opposite reaction. And we studied this a lot during statics class, right? So me sitting in this chair right now, gravity is pulling me towards the earth, but the thing that's preventing me from falling is the normal force of the floor pushing me back up onto the chair. And it's the balance of those two things that represent equilibrium in that case. We're going to continue talking about action and reaction this semester, but honestly, in a lot of cases, our forces aren't going to be balanced out perfectly because it's unbalanced forces that cause that acceleration and that motion that we're studying in dynamics. So first things first, what's the difference between mass and weight? Weight is the pull of gravity on an object. So I'm sitting here on Earth, gravity is pulling me towards the Earth, and if I was sitting on a scale, it would tell me how much I weigh. Mass is the amount of matter inside an object. So when we're talking about mass, it's basically adding up all of the atoms and molecules that make up an object. It has nothing to do with gravity. My mass here on Earth is the same as my mass on the moon, is the same as my mass on Mars. My weight for each of those locations is going to be different because the pull of gravity is unique to whatever planet or moon I might be standing on. We evaluate the difference between mass and gravity using this equation. This equation is basically a special form of Newton's second law. The type of force we're dealing with on the left-hand side is weight. I've got my mass there as a measure of inertia. And then the acceleration that I'm measuring here is acceleration due to gravity, or labeled as g. So weight is equal to mass times gravity. This is really the best way to be able to convert between weight and mass, is using this equation here. Talking about units, weight is a force, so it's going to have units like pounds in the English system or the US system, or newtons in the SI or the metric system. Mass is going to have slugs in the English or US system. It's going to have units of kilograms in the metric or SI system. We use kilograms, not grams, when we're talking about engineering. And then gravity, that's going to be everything we're going to analyze this semester is going to be on Earth. So gravity will either be 9.81 meters per second squared, or if we're working in the US or English system, we're going to have 32.2 feet per second squared. Okay? So if you're given weight and you need mass, use this equation. If you're given mass and you need weight, use this equation. Use this to convert between the two, and always make sure that you keep your units in the original unit system unless the questions asked you to convert it to something else. Okay? Too many dynamic students struggle with accurately converting between weight and mass. I'll mention little tips all semester long to try to help you prevent making those types of mistakes, because I don't want you to be the one student that misses that question on an assessment. So next, we've talked about force equals mass times acceleration a little bit. I want to talk next about how we can visualize this motion. If on the left-hand side, we talk about the sum of all of the forces, the way we visualize that is through the free body diagram. So in this case here, we've got a little particle here representing the center of mass of an object. And that center of mass has two forces acting on it, F1 and F2. When we add those two forces together, we get the sum of those forces, or the resulting force. And in this case, that resulting force is to the left. All of that comes out through the free body diagram. The free body diagram is the manifestation of Newton's second law on the left-hand side of the equal sign. On the right-hand side of the equal sign, we have a brand new drawing or diagram, and this is called the kinetic diagram. And all it is a manifestation of the right-hand side of Newton's second law. So what's the right-hand side? Mass times acceleration. So here's my particle, and here's a vector, and the magnitude of that vector is going to be whatever the mass is times its acceleration. Right now, in this chapter, our kinetic diagrams are going to tend to be pretty simple, but they're going to get more complex as the semester goes by. So I'd like you to get used to what a kinetic diagram looks like and what components form a part of it, so that when we get to those more complex problems later on, you're not learning this from scratch. The other thing that I want to mention here is notice the direction of these vectors. If my force vector is acting to the left, then my kinetic diagram has to show that mass times acceleration is also to the left. You can think of it as the force acting on the object causes the acceleration, or the acceleration is caused by the forces acting on it. They're one and the same thing. So from a vector equation standpoint, the direction of my forces has to be exactly the same as the direction of my mass times acceleration. So sum of forces is the free body diagram, and mass times acceleration is the kinetic diagram. On the assessment for this unit, you will be required to draw both drawings for at least one problem. So you need to practice this as a skill on your own. A lot of times in your third and fourth year classes, instructors are going to expect you to learn these skills, and they aren't necessarily going to give you practice work to do so. So to try to prepare you for your years 3 and 4 education, I am reducing the number of worksheets that you have to do. In statics, I would have given you some worksheets to practice your free body diagram skills, but I don't do the same thing in dynamics because I'm trying to get you to become a more independent learner. That doesn't mean that I'm not here to support you. If you have questions about either of these diagrams, I'd be more than happy to answer them for you. I'm also happy to go in and show you how to draw these drawings when we do examples, and like we'll do in a few minutes. So next one is, how do we draw a free body diagram? We draw free body diagrams exactly the same way that we did back in statics class. So in statics, what we would do is we would separate the object from the surrounding system. So here is a statics problem. In fact, I showed you this exact slide if you took statics with me in the previous semester. And in this case, we're studying the equilibrium of this knot here. So I'm going to separate this knot from the surrounding environment. I don't care that it's attached to this weight. I don't care that these ropes are attached to the wall. All I care about is what's going on with this knot right now. And then I'm going to draw a picture of the knot. Then the R stands for reaction forces. I'm going to represent this rope here on the upper left and this rope here on the upper right. And I'm going to represent those as force vectors for the tension in each of those ropes. E stands for external forces. The only external force I have in this particular situation is the weight. So I'm going to represent a force vector acting straight down to represent the weight of my object. The A stands for axes and angles that are relevant to the analysis. Right now, because all of my forces are concentrated on this knot, that is going to be my origin, and I just define my coordinate system as being positive x and positive y. Typically positive x to the right and positive y upwards. That's all you got to do, is just draw the coordinate system showing you the direction of positive motion. And then in terms of angles, we've got the angles for our two ropes here. I have theta 1 and theta 2. The last letter in spread is D, dimensions relevant to the analysis. We're going to really focus on this when we get to rigid bodies, because there we have to worry about rotation and moments. So we're going to need to know about moment arms. For right now, the dimensions really aren't very significant to our plan. Okay, so let's go ahead and practice this real quick for this example here. We're going to be using this word spread, S-P-R-E-A-D. S stands for separate, so I'm going to take this knot and I'm going to separate it from the rest of its environment. P stands for picture, so I'm going to draw a picture of my knot. So there you go, there's a picture of my knot. R stands for the reaction forces. Reaction forces meaning what are the things that are preventing motion. We talk about action and reaction. The reaction forces are the things that prevent motion. So if they don't exist, the object would move. So in this case here, my weight would fall if the two ropes at the top weren't holding it up. So those represent my reaction forces. So I'm going to have a reaction force over here. Ropes only are helpful to me in tension. So I draw my knot in tension as if it's being pulled up and to the left. I typically label my tension forces with the letter T, and then I'll go ahead and represent this as T1. On the right-hand side, I've got another force here. Again, it's in tension, and I'll label it T2. There are my reaction forces. E stands for external forces. These are the action forces of the action-reaction pair. So these are the things that are trying to make my knot move. The only thing I have for that is the weight of this object that's hanging down at the bottom of my rope. So that's it. Those are my external forces. A stands for axes and angles. All I need you to do is just draw me a coordinate system and define your positive x and positive y. That's all I need from you right now. This is going to change in the future, so you'll start to learn why we do these coordinate systems on these drawings to help us out with future endeavors. Then the other part of A, you got axes. Now we got to worry about angles. And for me, the two angles are already defined in the other drawing. This is going to be theta 2, and this guy right here is going to be theta 1. Axes and angles. The D, dimensions, will be more relevant once we get to chapter 17, so I don't really need to worry about dimensions at all at this point. So there you go. There's a high-quality free body diagram using the word spread. For kinetic diagrams, they are super duper simple. Okay, if I've got a crate right here with all these forces acting on it, I've got a free body diagram that shows all of the external forces. You've got, you know, the focus of your analysis, everything you need for a spread is on here. We separated the crate from its environment. We've drawn a picture of the crate. We've got the reaction forces. In this case, it's the normal force and the friction force. We've got the external forces, the weight, and this 400 Newton force acting on my crate. My axes, they didn't really draw that in this particular case. I adapted it a little bit from the way the book does it, but we would draw our coordinate system here at the center of mass of the crate. And then we've got the angles, the 30-degree angle here. So this totally meets the definition of a free body diagram. On the other side here, we've got our kinetic diagram. So the free body diagram is the sum of all of our forces. The kinetic diagram is mass times acceleration. So if my crate is 50 kilograms, and then I just multiply it by the acceleration. In this case here, we're assuming that the box is moving to the right. That's in the positive x direction, similar to what we saw for statics class. If for some reason your acceleration turned out to be negative, that negative sign would just mean that the default direction that you chose in your kinetic diagram was actually in the opposite direction to the real direction, which a negative sign would mean that the acceleration was to the left. That's all I need, is an acknowledgement of where the center of mass is, and then a vector that represents the mass times the acceleration of the object. You'll be required to do something similar to this for the assessment. Consider yourself warned. Okay, so let's go ahead and move on to our first example here. In this example, we have the coefficient of kinetic friction between the crate and the ground is 0.3. Determine the distance the crate travels and its velocity when time is equal to 3 seconds. The crate is going to start at rest, and the force P is 200 newtons. So let's go ahead and work on solving this problem. So first things first, first step in the problem solving process is we're going to create our drawing. And in this drawing, there's actually going to be two parts to it. You may have guessed it's going to be the free body diagram, and then it's also going to be the kinetic diagram. So for the free body diagram, I'm going to focus on just my box. So I'm going to remove my box from the surrounding environment. I don't care that there's a rope attached to it. I don't care that it's resting on a surface. I'm just going to draw a representation of my box. Okay. So that's separate the box from its surrounding environment and draw a picture of it. In terms of reaction forces, similar to the free body diagram we looked at just a couple minutes ago, I am going to have my normal force here. I am also going to have a friction force. That friction force is going to resist it trying to move to the right. Okay. In terms of my external forces, I'm going to have my force P acting up and to the right, and then I'm also going to have my weight acting straight down. So those are my external forces. In terms of the letter A, that's axes and angles at the center of mass. Just represent your coordinate system, positive x, positive y. And then the other thing that you want to represent here is going to be your angles, which is 30 degrees. And then for our purposes, we do not need to worry about dimensions at all. Okay. When it comes to our kinetic diagram, we are going to basically represent, all right, change my, represent the center of mass. You can also draw, I like to draw my crate just so that my kinetic diagram looks exactly the same as the picture in my free body diagram. And then you're just going to draw from that a representation of the mass times the acceleration. In this case, the acceleration is going to be in the x direction only. Another thing you can do here, and this is a matter of personal preference, while you're thinking about acceleration, you may want to note that a sub y is equal to 0, because you can recognize that there is no motion in the y direction. So that can be helpful as well. Oops, sorry about that. Pulling up my solution here so that I can remember my calculations for what we do in a couple minutes. Okay, so now that we have our two drawings done, let's go back up and revisit this problem statement. So now I want to think about, what do I know about this problem? The coefficient of kinetic friction, denoted as mu sub k, is 0.3. So this is Greek letter mu, mu. Sub k means that it's kinetic friction. So kinetic friction is friction of motion. In statics, we dealt with static friction for problems that were in equilibrium. So a good portion of this class will be studying kinetic friction rather than static friction. They tell me the mass of my block or my crate is 50 kilograms. So I'm going to need that later. And then the other thing that they tell me is that the crate starts from rest. So that means my original velocity is 0 because it is at rest. They also tell me that the value of P is 200 newtons. So that's everything that I need to know to solve my problem. And then for the unknowns, what I'm looking for here is, it says, tell me the distance the crate travels. So that's the variable S. And what is the velocity? And both of these are at a time of 3 seconds. So that's what I'm trying to solve. Come down here and start working on my solution here. Talk about equations and math. And my overall overriding equation here is going to be to sum the forces, and those are going to be equal to mass times acceleration. When we think about this equation, if that's the vector form of the equation, I can break it up into two scalar equations. If I sum my forces in the x direction, that should equal to mass times acceleration in the x direction. And if I sum my forces in the y direction, that should be equal to mass times acceleration in the y direction. So this is the vector form. And then these are the scalar forms. And the scalar forms, notice that I have two independent linear equations. That means I can solve a system of equations for up to two unknown values. As we talked about before, this guy we get from the free body diagram, and the right-hand side we get from the kinetic diagram. Okay. So we're going to basically develop a series of equations here that we're going to use to solve this problem. Go back to my free body diagram. The first thing I want to do is write my equation for forces in the x direction. But before I can do that, I need to recognize that my force P needs to be resolved into x and y components. So I need to do that step first before I can write my equations. So my force P is equal to 200 newtons, and it's going to have an x component and a y component, and it's at an angle of 30 degrees. Notice that when I draw this as a vector triangle. It's not a triangle from trig class. This is vector math that we're doing here. I like to draw arrows at each vector because it's one way to signal to our brain whether or not a component in the x or y direction is a positive component or a negative component based on how we've drawn our coordinate system. My triangle is a right triangle, so that means I can use sine, cosine, tangent, Pythagorean theorem in order to solve it. So if I want to find the p sub x component of this, p sub x is going to equal to the force, 200 newtons, times the cosine of 30 degrees. It's going to be in the positive direction because it's to the right. P sub y is going to equal to 200 newtons times the sine of 30 degrees. Okay, so now that I have those two components of the force, I'm ready to come down here and write my first equation. So if I sum my forces in the x direction, I'm going to have P sub x that I just found. And then the other force that I'm going to have is I'm going to have my friction force here. So right now I'm just going to write that my friction force is in the negative x direction, and that's going to equal to my mass times my acceleration in the x direction. You could also describe this as being 50 kilograms times a sub x, because we know what our mass is from the problem statement. Right now, I don't know what my friction force is, and I also don't know what my acceleration is. So I have one equation and I've got two unknowns. So I'm right now just going to label this as equation 1. That's a signal that I use to manage my work so that I know that I have to come back to this equation at some point. Then I'm ready to go in and find my forces in the y direction. Visit my free body diagram again. I'm going to have my P sub y component acting up. I've got my normal force acting up, and I've got my weight acting down. So P sub x plus my normal force minus my weight. That is going to equal 0. Okay, I didn't discuss this in the x component, but I get the information from my right-hand side from my kinetic diagram. So whatever my mass times my acceleration in the x direction is, and then I know that there's no motion in the y direction, so a sub y is equal to 0. Another way we can describe this is my force equation in the y direction is in equilibrium, even though my particle is moving in the x direction. Okay. So to evaluate this one a little bit further, next thing I need to do is I need to calculate my weight. We talked about that. Weight is equal to mass times gravity. My mass is 50 kilograms. Gravity for the SI or metric systems, 9.81 meters per second squared. Calculate that. It should come out to 490.5 newtons. Okay. So I can write that equation. If this is equation number 2, I can revisit equation number 2 here. It's going to be 200 times the sine of 30 plus my normal force minus my weight. Okay. And then I can basically do algebra here to isolate the normal force on one side of the equal sign. And when I do that and run it through my calculator, I should get my normal force is 390.5 newtons. Very important point right now. I calculated that my weight was 490.5 newtons. I calculated that my normal force is 390.5 newtons. 390.5 is not the same as 490.5. A really, really important thing here is my normal force does not equal my weight. A lot of students become pattern trained in physics because the problems are on the simple side. We think that the normal force is always equal and opposite to the weight. In our class, that's only going to be true in very specific instances. More often than not, your normal force is going to be something other than the weight. In this case, think about where, think about where we came up with this. This 395 came up with taking our weight and then subtracting the y component of our tension in our rope. So you got to be really, really careful here. You get into a big rush, you assume normal force is equal to weight, and you go on and finish the solution, and the solution is wrong because you made a wrong assumption. Okay, so we've exhausted what we can do with equation number 2. We got to go back and revisit equation number 1. For equation number 1, we need to figure out what we're going to do with this friction force here. I know that my friction force is going to be my coefficient of kinetic friction times my normal force. My coefficient of friction was 0.3 in the problem statement. I now know that my normal force is 390.5. I go in and I calculate that, and I get about 117 newtons for my friction force. So now I can come up here and rewrite my first equation, and I can say 200 newtons times the cosine of 30 degrees minus my friction force is equal to my mass times my acceleration in the x direction. Do my calculator work, and I get a sub x is equal to 1.1211. My units will be meters per second squared. So, couple quick things I want to mention about this solution. The first thing is notice that this is a positive sign. That means that the kinetic diagram is correct. If I did the math here and I turned out with a negative sign, it would mean my actual direction of my acceleration was in the opposite direction to what was shown in the kinetic diagram. So that's the important first lesson. The second one is about units. We've learned something or review something that we learned in statics class. If F is equal to ma, we know that units of force is newtons. We know units of mass is kilograms, and we know units of acceleration is meters per second squared. So what we get from this is 1 newton is equal to 1 kilogram times meters per second squared. Just like we have to convert between weight and mass, we also have to be able to convert between units of newtons or force with units of mass times acceleration. So you can always confirm that your units work out by remembering this conversion factor here. Okay, so we found acceleration. Let's go back and check our original problem statement. Our original problem said, I don't want to know what the acceleration is. I want to know what is position times velocity. And this is where we make connections between what we've learned back before in chapter 12 to what we're learning about now. The main reason why we use this overriding equation of the sum of forces is equal to mass times acceleration is this obviously tells us about forces on the right-hand side, and on the left-hand side. On the right-hand side, it tells us about motion. We get our knowledge of forces from statics. We get our knowledge of motion from chapter 12. So typically for problems involving Newton's laws of motion, we're either given a ton of information about forces like we were in this problem, and now we want to solve for motion, or we're given tons of information about motion and we want to solve for forces. In our case, we were given the forces, so now we want to use it to find acceleration. We did that, but now that we know something about acceleration, we can bring all of the tools of everything we learned in chapter 12 to learn a little bit more about the acceleration and the motion of my crate here. So to do that, let's remember what we learned about chapter 12. My acceleration is constant. So if you go back to your equation sheet for chapter 12, you'll notice that there were 3 equations that we had for constant acceleration. The one that's going to help us with finding position ends up being change my color. S is equal to S sub O plus V sub O t plus 1/2 A sub C t squared. I'm looking for my final position. I'm starting at the origin. My initial velocity is at rest. My acceleration I just found. And I want to know how far has it gone after 3 seconds. Little word of caution, don't forget the squared here. A lot of students tend to drop that exponent when they're substituting their values in, and then it causes a mistake in your solutions. I go through and I calculate this, and I should end up with S is equal to 5.0450. That'll have units of meters. The second squared over second squared cancel each other out. Remember that position is technically a vector quantity. So its position is going to be to the right of the origin, or to the right of where it started from. To find the final velocity, we need the second equation from chapter 12. And that's going to be v is equal to v sub o plus a sub ct. V is equal to, it starts at rest. I calculated my acceleration a little while ago, and I want to know what is the velocity after 3 seconds of travel. That results in 3.3633 meters per second. So now I can describe my velocity here as 3.36 meters per second. Turned out to be a positive value, so that is going to be to the right. And there you have it. Okay, so let's move on and talk about a second example here. In this example here, we have 2 blocks. Those blocks are connected with a spring. We have the weight of each of the blocks provided. They're resting on a surface, and we know what the coefficient of kinetic friction is for that surface. They give us the spring constant for our spring here in the middle. And then it tells us that it's compressed a total of 0.2 feet. And what we want to know is what's the acceleration of each block right after it is released. So let's go ahead and tackle this example. Just like I did in the last example here, I'm going to start out with a drawing. In my drawing, I'm going to draw a free body diagram and a kinetic diagram. Okay. I'm going to go ahead and do this for each block independent of the other. So for my first free body diagram, I'm going to focus on block A. Separate block A from the surrounding environment. I don't care about the surface, the spring, or the other block. I just care about the block A. That makes all of the other forces external to block A. Draw a picture of block A. In terms of reaction forces, the things that are preventing it from moving, I'm going to have a normal force for block A. And if we think about the spring being compressed, once it's let go, block A is going to move to the left. Friction opposes motion, so that means my friction force is going to be to the right. External forces, I've got my weight for block A, and then I'm also going to have my spring force, and that's the thing that is pushing my spring to the left. In terms of my kinetic diagram, at the center of my block here, I'm going to do something that might seem a little counterintuitive to you, but there's a method to my madness, so just trust me. I'm going to draw my mass times acceleration to the right. And the reason why I do that is because I prefer to do this and let my negative sign at the end tell me it's actually to the left, then assume it's to the left and then struggle with plus minus signs when I'm solving the problem. So even though I know that intuitively my block is going to move to the left, I prefer to show my acceleration in the positive x direction. Okay. I did not draw it. I should have by axes and angles. I don't have any angles, but I should still show my coordinate system. So there you go. Block diagram, or excuse me, free body diagram and kinetic diagram for block A. For block B, I want to do the same thing. So there's block B. I'm going to have my normal force for B. My force is going to move, my spring force is going to move it to the right. So that means my friction force is going to be to the left. External, I'm going to have my weight of block B. And then I'm going to have my spring force pushing it to the right. Axes and angles. Pretty simple for right now. And then just come over here and capture my free body my kinetic diagram And I'm going to go ahead and show this one as mass of block B times A sub x. I'm going to actually change this up just a little bit. Apologize for making the corrections for you, but I want to make sure that this is clear to everybody. It should be mass of A times acceleration of A, mass of B times acceleration of B. Okay, I changed those subscripts for a reason. One is my two blocks weigh different, so they're going to have different masses. And we got to recognize that the acceleration of each of these blocks is going to be slightly different. Why? Because they aren't the same mass. So the acceleration is going to be different. Okay, so something that we need to think about there. Okay, we got through that part of it. So go down here to our, sorry, we didn't do our knowns and unknowns. So knowns. The weight of block A is 8 pounds. The weight of block B is 6 pounds. U sub K for both of them is 0.2 pounds. My spring has a stiffness of 20 pounds per feet. And it is compressed. What that means is that is S. S is the final length minus the original length. So once I've taken that difference is 0.2 feet. In terms of my unknowns, what am I looking for here? I want to know what is the acceleration of A and the acceleration of B. Okay. So now that I've done all of that, I'm ready to write my equations and do the math to find my solution. Okay. So let's start by working on block A. Sum my forces, set those equal to my acceleration, mass times acceleration. If I sum my forces in the x direction for block A, what I have in the x direction is F sub s is in the negative direction, and then my friction force is in the positive direction. So my friction force for A minus my spring force is equal to M sub A sub A. Okay, here's equation 1. Right now, I don't know my spring force. I don't know my friction force. I do know my mass. Or no, I don't know my mass. There was given weight, so I have to calculate my mass. And then I'm also given my acceleration. So I don't know what any of these variables are until I start doing some calculations. So let's look at each one in turn. Whoops. My friction force for A is going to be mu sub K times my normal force for A. I know that mu sub K is 0.2, but I don't know my normal force yet. I haven't found it. So there's a second equation I can't solve. Friction force, or excuse me, spring force, that's going to be K times S. K they gave me was 20 pounds per foot. S is 0.2 feet. Multiply those two and I get 4 pounds. Finally, something I could solve. Weight is equal to mass times gravity. So M sub A is going to be weight of A divided by gravity. The weight for block A was 8 pounds. Gravity is going to be 32.2 feet per second squared. Don't use 9.81 in the English system. That's going to equal 0.24845. The units will be slugs because that's the unit of mass in the English system. Notice that I have carried this out to 5 decimal places. I don't round to 3 until I'm rounding my final answer so that I don't induce too much rounding error too soon. Okay. So I still need my normal force. I can't solve for my acceleration until I find my normal force. And in order to find it, I need to sum my forces in the in the y direction. Go back to my free body diagram in the y direction. Make sure I'm looking at the right block here. My weight is acting down and my normal force is acting up, and that's all I have. My weight is acting down, my normal force is acting up, and there is no acceleration in the y direction. So here's one of those specific instances where my normal force is equal to my weight, or 8 pounds. Don't assume, confirm. And you confirm it by summing your forces in the y direction. Okay, so now I can revisit equation number 2. My friction force for block A is going to be 0.2 times 8 pounds, which will be 1.6 pounds. Revisit equation 1. My friction force is 1.6 pounds minus my spring force is 4 pounds is equal to my mass, which is 0.24845 slugs, times A sub A. I end up with A sub A is equal to a negative 9.650. This will be in feet per second squared. Couple things here. This negative sign means that the kinetic diagram is opposite to the correct direction. So if I wanted to describe this as an acceleration of block A as a vector, I would call this as 9.65 feet per second squared, and my acceleration would be to the left. Okay. The other thing I want to point out here, similar to the last example we did, is this guy here. F equals ma. In the English system, force is equal to pounds, and mass is equal to slugs, and acceleration is equal to feet per second squared. So 1 pound is equal to 1 slug times feet per second squared. So we're going to need to use those conversions back and forth, just like we convert between weight and mass. We need to be able to convert between pounds and slugs and feet per second squared. Okay. All right, so there's the acceleration for block A. Let's go on and do the same thing for block B. At this point, I would challenge you to pause this video, try to see if you can solve block B for yourself, and then restart the video and see if you come up with the same answer that I did. I'm going to go ahead and continue on with solving for it. So for block B, here we go. I'm going to go ahead and just use a little magic that I can do on my iPad, and I'm going to copy this drawing down because it'll make it a little bit easier for us to write our equations. Here we go. Love my iPad. Sum my forces in the x direction. I have my spring force acting to the right, which is positive. I have negative friction force for B, and that's going to equal to the mass of B times A sub B. And here, I'm going to go ahead and relabel this equation 1 because I'm starting over from scratch. I do know my spring force. My spring force is going to be the same as it was up above. So my spring force here is going to be 4 pounds. That's the same. There's one spring. That spring is compressed oh so much, and it acts on both blocks. So it's going to provide the same force on both blocks. Okay. My friction force is going to be same friction coefficient, but I don't know my normal force for B. Note, N sub A does not equal N sub B. And we're going to prove that in just a minute. So don't make that mistake. Mass. Take the weight of B, divide that by gravity. So the weight of B was given to us as 6 pounds, so it's a little lighter than block A. Divide that by 32.2 feet per second squared. 0.18634 slugs. I need to find my normal force so I can find my friction force. So my force is in the y direction. I'm going to have my normal force for B minus my weight for B, right? That's getting that straight from my free body diagram right here. Weight acting down, normal force acting up. That's going to equal 0 because there is no motion in the y direction. So my normal force at B is equal to my weight at B, and my weight at B is equal to 6 pounds. Okay. So if my friction force is equation 2, I can now revisit equation 2. My friction force for B is equal to 0.2 times 6 pounds, or 1.2 pounds for my friction force. Now I can come down here and revisit my first equation. Fit everything on here at once. Spring force is 4 pounds. Friction force is 1.2 pounds. That's equal to my mass, which is the 0.18634 slugs, times A sub B. That tells me that A sub B is equal to 15.027 meters per second squared. Or if I call A sub B as being a vector, it's 15.0, I'm sorry, not meters, feet per second squared. Notice that my solution is positive, so that means B is moving to the right. And there you go. There you have it. Okay, I do have one more example that I would like to get through for today's class, because I think each of these 3 examples I'm showing you shows a progression of the level of complexity that we can get for problems like this. I like this one because it shows a true engineering example here where we've got some parts of this mechanism that are moving and then other parts that are static. They're made to be in equilibrium. I am looking at the clock here, and my guess is that this video is going to run a little bit more than the hour and 25 minutes that a typical class meets for. So I apologize for the extra length in this video, but I think it's going to be worth it for you in the long run. So let's go ahead and take a look at this last example. So in this example, we've got a motor that's described right here, and it's lifting a crate that's 50 kilograms, and that crate has an acceleration of 6 meters per second. What we want to know is what are the components of the reaction and the couple moment at the fixed support here at point A. So in statics class, we may have had this crate hanging at point B, but the crate would have just been stationary. It wouldn't have been moving. So I really like this problem because it makes us revisit a few concepts from statics, but then it adds the complexity of the fact that the crate isn't static anymore. It's now moving. And not only is it moving, but it's also accelerating. So just like I've done in the past, I'm going to go ahead and draw a couple of free body diagrams. The first one I'm going to draw is of the crate itself. So my drawing, I'm going to draw a free body diagram of the crate, and then a kinetic diagram of the crate. So free body diagram of the crate is going to be really simple. There's my crate. In terms of reaction forces, I have the tension force preventing it from falling. And then for action forces, I have the weight of the crate. So separate the crate from its environment, draw a picture of it. What are my reaction forces? What are my action forces? The only other thing I need to contend with is my axes. And since everything for the crate is perfectly up and down, all I have to do is say up is positive. In terms of my kinetic diagram, go ahead and draw my crate here. And my kinetic diagram, I'm just going to show mass of the crate times A of the crate. There we go. That's all I need for my kinetic diagram for the crate. The next thing that I want to do is I want to take a look at my fixed support here. And for my fixed support, I've got this long beam. I've got point A on the left-hand side, point B on the right-hand side. Okay. I have right here a little pulley system. That pulley is free to rotate on a pin joint. So I'm going to draw a separate free body diagram for my pulley system. For my pin joint, though, I know I have, this is a machine from statics class, and a pin joint, I know that it resists motion in the right or left. It also resists motion up or down, but it does allow it to rotate. So on B, I'm going to end up with reaction forces of Bx and By. Okay. On the right-hand side of my beam, they say it's a fixed support. A fixed support doesn't allow any motion. So over here, I'm going to have an A sub x, an A sub y. I will also have a moment reaction at point A. Notice that I've drawn all of these reactions in the positive direction. I also need to draw my axes and angles. I'm going to sum my moments at point A, and I don't have any moments. The other thing that I do need, recognize that this is a rigid body. It's got size and shape that matters. I'm going to have to calculate moments in a bit, so I need to calculate my moment arms. And in this case here, the moment arm I care about is the fact that this guy is 4 meters long. And I got that directly from this. This beam here is in static equilibrium. It is not moving at all, so I don't need a kinetic diagram for it. Last free body diagram I need to draw is for my pulley system. So there's my pulley. This is another part of the machine. If you remember from statics class, at the end of statics class, when we're dealing with this machine, we have to break down the components into each individual piece part. And where they meet, we need to have action-reaction pairs. So what that means to me is if I drew Bx to the right here, I'm going to have to draw Bx to the left here. So that when I add this force and this force together, when I put Humpty back together again, all of the pieces add up to 0. I apologize for that reference. Anybody familiar with the nursery rhyme? Humpty Dumpty sat on a wall, Humpty Dumpty had a great fall. Okay, that was where that reference came from. All it means is that the BX's have to cancel each other out. That's what I should have said. Similarly, if BY is up, then BY needs to be down here. Okay. Other action forces on my pulley, I'm going to have my tension forces here. Tension is going to be pulling down this way, and then it also is pulled out to an angle right here, and they gave me that angle on my original drawing of 30 degrees. So I need to show this angle here of 30 degrees. Okay, there's my 3 free body diagrams. Come back up and revisit this, figure out what we know. The motor lifts a crate, so I know the mass of my crate is 50 kilograms. The acceleration of the crate is 6 meters per second squared. Notice in the drawing that they tell us that the acceleration is up. And then in terms of things that are unknown, what am I trying to find? I want to know what are the components of the reaction force and the couple moment at A. So what is AX? What is AY? And what is the moment at A? Those are the things that I'm trying to find. So I should notice that I've got 3 unknowns, so I need at least 3 equations. We're going to actually visit more than that. Okay. So equations. Okay, let's see if we can get this going. Let's go ahead and analyze the crate first. It's the simplest one. Although it's got a complication, so it might not be the simplest one if you don't pick it up. A lot of students, by drawing just free body diagrams, or maybe not even drawing a free body diagram, just looking at it, are going to say, oh, well, the tension's equal to the weight, right? Because that's what the free body diagram shows. And they're thinking with their statics brain, well, those two forces have to be equal and opposite to each other. Until we recognize that we've got this thing. The sum of the forces for my crate is not equal to 0. It's equal to mass times acceleration. And that little tiny complication is going to show us that the tension force is not equal to the weight. It's equal to something else. So let's do that. So when I do my crate, sum my forces in the y direction, I'm going to have the tension acting up. I'm going to have the weight of the crate acting down, and that's going to be equal to the mass of the crate times the acceleration of the crate. They gave me the mass of the crate. They gave me the acceleration of the crate. What I don't have yet is the weight of the crate, which is going to be the mass of the crate times G. The mass of the crate was 50 kilograms. G is 9.81. That's going to give me 490.5 newtons. So now I can revisit this first equation and do my substitutions. I need to know what is that tension force. Subtract off my weight. That's equal to the mass. They gave me my acceleration as 6 meters per second squared. That is going to show me that my tension force isn't just 490.5, the weight. It's going to be 490.5 plus the product on the other side, and that ends up being 790.5 newtons. So that is my tension force. Okay. Next, we're going to analyze our pulley. So let's revisit that free body diagram. So for my pulley, got to recognize that this tension force here, this tension force is the same tension force that we just solved for. Okay, there's one rope and it's going to have the same tension all throughout the entire rope. Think about it. If the tension was different in one spot than in another, that means my forces are unbalanced, and that means that my cable has broken. Or if it's less in one area than another, the rope can become slack, and then it's not in tension anymore. So I need to have one consistent tension throughout my entire rope. Okay. So by saying that, I need to take this guy right here and I need to figure out what are the X and Y components of this tension force. Once I do that, then I can analyze this entire thing here. Okay. So first I need to resolve that tension force for my pulley system. So I know my tension here is equal to 790, whoops, can't even write, 790.5 newtons. I'm going to have a T sub X and a T sub Y, and this is going to be 30 degrees on a normal, or excuse me, a right triangle. T sub X is going to be in the positive direction. It's going to be 790.5 newtons times the cosine of 30 degrees. T sub Y is going to equal negative, because it's acting down, my tension force times the sine of 30 degrees. Okay. Sum my forces in the X direction for my pulley system. And I'm going to have B sub X over here acting to the left, and then I'll have my positive T sub X component. So negative b sub x plus the 790.5 times the cosine of 30. My pulley is not moving, so its acceleration is 0. So that gives me b sub x is equal to a positive 684.59 newtons. So that is going to be to the right. Some forces in the y. I'm going to have negative b sub y, negative t, and then a negative component of tension in the y direction. So negative t is going to be a negative 790.5, negative b sub y, negative y component, and again, my pulley is not moving, so it is set equal to 0. Solve for that. B sub y ends up being a negative 1185.75 newtons. That negative sign means that b sub y is actually acting down, opposite to the direction, or excuse me, my bad. This is why I don't like doing things this way, okay? B sub y was down, so a negative sign means that b sub y is actually acting up. So easy to make those mistakes. Okay, we analyze the crate, we analyze the pulley. Now for the very last thing, we got to come up here and analyze my analyze the beam here. I'm going to go ahead and copy this guy down, make it easier to write our equations. Now we're analyzing the beam. Beam is in static equilibrium. Everything adds up to 0. Okay, so sum my forces in the x direction. I have a sub x plus b sub x. I know that b sub x, I just found it, was 684.59 newtons. It turns negative when I move it to the other side. That negative sign means that this direction is incorrect, that the actual direction is to the left. So a sub x is 684 engineering rounding rules to the left. Sum my forces in the y direction. I've got a sub y plus b sub y. So a sub y is going to equal to a negative b sub y, but notice that b sub y is already negative, so it's a negative, negative. So a sub y here is going to be a positive 1180 newtons, acting up. Again, engineering rounding rules. Last one, sum my moments. May have been a while since you've done a moment equation from statics class, so let's tackle this. I chose summing my moments about point A, and the reason why I do that is a sub y intersects a sub x intersects A, so that means the moment arms for these two guys is 0, so these do not create any kind of moment about point A. B sub x, principle of transmissibility, says I can move this force back and forth, and if I move it far enough to the left, it's going to intersect my origin here. So B sub x has no moment arm, so its moment is 0. So the only things that cause a moment are B sub y, which is 4 meters away from A, and this moment here. I've drawn that in the positive direction. So sum my moments. I have the moment about A, that's the reaction moment about A, plus B sub y times 4, whoops, not 9 meters, 4 meters. So M sub A is going to equal negative B sub y, and we calculated B sub y was this negative 1185.75 newtons times 4 meters. Okay. And that ends up equaling 4743 newtons times meters. Okay, sorry here, I'm pausing here because I thought I noticed a mistake in my solution. So let me just double check my work here. Ah, that's where the mistake came from. I did make a mistake on my solution here. It's where it's so easy to make these mistakes. When I was focused on my pulley, I showed that B sub y was acting up. Okay. My beam showed that my force was acting up, but this must be opposite to the direction shown up here. So that means that in actuality, this force is acting down. Okay. And by saying that, what that means is that by acting down, this is going to be a negative moment. How do I say this? No, it's all good. It's all good because of the fact that I created my negative sign here and I had my negative sign here. Well, these two negatives become a positive. So what this means to me, I just had to think through this, is that that positive sign means that the free body diagram is correct and that M sub A is counterclockwise. Okay, I just had to think through that a minute. So M sub A is going to be 4740 newtons times meters counterclockwise. And there we go. All right. So I know this video ran a little bit long, but I hope that these examples were useful to you. Please reach out if you have any questions. Otherwise, good luck with the homework set for this. Good luck.